So, let us resume our discussion on the minimum spanning tree algorithm. We were looking at the Gallagher-Humblett-Spira algorithm, and the algorithm, just to recap, starts with each node as a one node fragment. The nodes in a fragment cooperate to find the lowest weight outgoing edge of the fragment, and when the lowest weight outgoing edge of a fragment is known, the fragment will be combined with another fragment by adding the outgoing edge in cooperation with the other fragment. Okay. The algorithm terminates when only one fragment remains. Okay. So, we were looking at the summary of the combining strategy. So, there are three rules basically. The first rule is that if the edge EF, which is the lowest outgoing lowest weight outgoing edge from F, if it leads to a fragment F dash which has a level larger than the level of the fragment F, then the fragment F combines into F dash, after which the new fragment has name Fn dash, that is the name of the larger fragment, and the level L dash. Okay. And these new values are sent to all processes in F. The rule B is if the two fragments have the same level, then the two fragments combine into a new fragment with level L plus 1, and the weight of the new edge which is added to join the two fragments, that edge is called the core edge, and the weight of the core edge becomes the name of the integrated fragment. Okay. This is the rule for combining two fragments at the same level. And the third rule is that in all other cases fragment F must wait until rule A or B applies. So, for example, if a large fragment, a fragment at a higher level, finds that the edge which is the minimum weight outgoing edge from that fragment leads to a fragment which has lower weight, then the larger fragment will wait. It will not immediately join with the smaller one. Okay. And the reason for this waiting will become apparent as we go through the algorithm. These are some of the data structures which are maintained by the algorithm. One is this STACH, it stands for status of channel. Okay. The status of channel from P to Q, this is maintained at the node P. So, node P maintains the status of the edge PQ. The status is branch if the edge is known to be in the minimum spanning tree. It is reject if the edge is known not to be in the minimum spanning tree, and is basic otherwise. So, initially it will be basic. When we decide that it is part of the tree, we will make it branch. On the other hand, if ever we find that that edge is between two nodes already in the tree, then we will say that that edge is reject. Okay. So, it will change status only once, every edge will change status only once. It will go from basic to either reject or it will go to branch, okay, or maybe none of them, but that we will see. Further P is for each process P in the fragment, further P is the edge leading to the core edge of the fragment. Now, let us understand this thing, that the algorithm is working by joining fragments, right, and when we join fragments we always refer to a core edge of the fragment. What is the core edge of the fragment? The core edge of the fragment is the edge which, so if two fragments of the same level join, then that edge is the core edge. Okay. If a smaller fragment joins with the larger fragment, then the core edge of the larger fragment is the core edge of the integrated fragment. Okay. So, that there is always a designated core edge of the fragment, and all the parent pointers of the nodes point towards the core edge, alright, except for the nodes which are adjacent to the core edge. Okay. So, you can think of the fragment as two subtrees joined by the core edge, and all nodes in this subtree point to this node, all nodes in this subtree point to this node. So, they all point towards the node leading to the core edge, alright. That is how it is going to be. There is no one root as such, okay. The core edge is like the root, okay. So, father P is the edge leading to the points to the edge leading to the core edge of the fragment, and state P of a node can be found if P is currently engaged in the fragment search for the lowest weight outgoing edge and is found otherwise, okay. So, when the fragment is searching for the lowest weight outgoing edge, then the status of the node P is find, and when it has found the lowest weight outgoing edge, its status is found, okay. And initially it is in the state sleep. So, these are the states of the process. We are going to look at this algorithm in three parts to make it easier to understand, okay. The first part is like this, okay. Again, you remember that any distributed algorithm is specified in terms of a set of actions, right. So, we are going to have these actions 1, 2, 3, 4 like that. Let us go through the data structure once again. State P, as I said, can be sleep, find or found. The status of channel P, the channel from P to Q, which is stored in P, can be basic, branch or reject, and we will have such status for each Q belonging to the neighbors of P, right. So, I will have for each neighbor a status of the channel to that neighbor, and that status can be basic, branch or reject. We are going to use name P as the name of the fragment and best weight P as a temporary variable to store the weight of the best edge weight that P knows about. So, it may not be one incident on it, it may be something which some of its children somewhere has found out, okay, and that is getting propagated towards the root, okay. So, we will see when we come to the usage of this what this variable does. Level P is the level of the fragment to which P belongs. Test CHP is a again pointer to a neighbor along which we have sent a test message to determine whether an edge belongs to the same fragment or belongs to a different fragment, okay. And best CHP is the pointer towards the best outgoing channel, okay. And father P is the pointer pointing towards the core edge of the fragment, and rec P is a counter where we will count the number of messages received when searching for the best weight outgoing edge, okay. That we will use in, I will again reiterate at the point of time when we use that, okay. You do not have to remember what each of these means right now. As you go through the algorithm, it will become fairly obvious how we are using this. Beg your pardon? The best weight P is the weight of the best outgoing edge from the subtree of this fragment. So, P is the root of some subtree in the fragment. So, best weight P is the best weight of an edge that has come up from this fragment. Not clear? This is P, this is P, okay. There is a subtree rooted at P which consists of the subtree of the MST so far rooted at P. There may be other nodes, ahead of this in the tree. So, this may be the whole fragment, but for P there is a subtree. Now, among the nodes that are there in P, you have these outgoing edges. Out of these weights of these outgoing edges, the best one, the weight of the best one will be stored in best weight P, okay.
Best channel
and base channel P is the pointer to the child through which you can reach that. Clear?
All these links be outside the fragment, none of them within the fragment.
No, within fragment any edges will be rejected once they are discovered, because they can never be part of the tree. Okay. So, let us return to the statement of the algorithm. So, this is the initialization code. Every process which starts the algorithm or which gets initiated into the algorithm, they will first execute this. So, even if a process is woken up by a message from its neighbor, it will first execute this and then process the message. Clear? On waking up, the process will first do this and then do anything else. Okay. So, let PQ be the channel of P with the smallest weight. Okay. So, the node, what does the node do? It looks at the channel with the smallest weight incident on it. It starts by saying the status of channel P to Q is branch. Okay. Level P is 0. How can we with certainty set this as branch? Because for every node, the minimum cost edge incident on that node has to be part of the tree. Why? Because you can think of the partition where this node is on one side and rest of the nodes is on the other side. So, the minimum cost edge incident on this node will have to belong to the minimum spanning tree, right. So, we set that edge to be a branch edge, which means it is part of the spanning tree, okay. And because this is a single node, we set level P equal to 0. We set state P equal to found, because you have already found the minimum cost outgoing edge, okay. You set rec P equal to 0, this counter it will become apparent what we do with this counter in due course of time, and then we send a connect 0 message to Q. This 0 is the level, because level P is 0. So, we are sending a connect 0 message to Q. Okay. Is that clear what a process on waking up does? When it wakes up, it examines its outgoing channels, finds out the minimum cost outgoing channel, it knows that this channel has to be in the MST. So, if Q is on the other side of the channel, it sends a connect message to Q with its own level, and what is its own level? 0, because this is a level 0 node, it is a single node fragment. Okay.
So, that status channel is also a branch, because you are going to be starting with a single node only initially.
Yeah, you can do this only for the single node.
You don't have to check intuitively that it is the branch, you like say because it is the minimum weight, because it is only single node, every edge going will be a branch only.
No. Then you are saying that for every node all incident edges will belong to the tree. No. Yeah, only the smallest weight one will definitely be there. More edges may belong to the tree, but at this point of time we do not know whether they will belong to the tree or not, right.
So, more edge incident on that node.
Yeah. See, when you have a node P, okay, this is the rest of the nodes. Now, if you look at the edges incident on P, the one which is the minimum cost among this will definitely belong to the tree. Why? Otherwise, we can remove the other edge and put that edge and reduce the cost of the tree. Right? So, we had seen this. Not clear? We showed just now, isn't it, that if you have S and T, then the minimum cost, the among all edges from S and T, the one which has the minimum cost will definitely have to belong to the minimum spanning tree, that we have shown. So, the minimum cost edge among these will belong to the tree, clear. Now, more than one such edge can belong to the tree. For example, it may so happen that this is the actual graph. So, this belongs to the minimum spanning tree, but then this also has to belong to the minimum spanning tree. But at this point of time we do not know that, but what we definitely know is the one which has the minimum among these will definitely belong to the minimum spanning tree. So, that one we are labeling it as a branch straight away and sending a connect message from P to Q. Okay. Now, upon receipt of a connect L message from Q, this is what we do. If L is less than level P, so this is P is receiving a connect L message from Q. Okay. What will P do? P will check what is the level of the message that has arrived. So, the level is less than its own level, then it will allow the smaller fragment, the lower level fragment to combine with it. So, what is it going to do? It will set the status of the channel to Q as branch, and it will send the initiate message to Q. What are the things that the initiate message will contain? It will contain the level of P. Why? Because every node in the subtree of Q will now change to level P. Every node in the subtree of Q will change to name P, the name of the fragment, and every node in the subtree of Q will inherit the state of P. What do we mean by the state of P? If P was currently engaged in searching for a lowest cost outgoing edge, then this fragment subfragment rooted at Q will join that search. They will join that search. This is the larger fragment. Okay. This is P, right. This is Q. Q is the smaller fragment. Q has sent a connect message to P. Okay. Now, what will P do? P will send an initiate message to Q with the level, with level P, with name P and state P. Okay. What are we going to do with level P? We will propagate that to this tree. Everyone will inherit level P as the level, everyone will inherit name P as the name, and everyone will inherit state P as the state. So, if it was the case that this fragment at that point of time was engaged in searching for a minimum weight outgoing edge, then these nodes will also join in that search. They will also start looking for minimum weight outgoing edges, right, because now this is an integrated fragment. This fragment should find out the minimum weight outgoing edge of the whole fragment, not only this part.
But sir, synchronization of Q, it has actually already found out the minimum edge.
It has found out and it has joined.
Yes.
After joining,
The next minimum edge.
yes, because this was engaged in that search. Now, this becomes integral part of this fragment. So, they must also join the search. Could be, that is why they have to join the search, right. Which one? This one?
Yes sir, that will be minimum because all
No, this one is already joined. This one has been already accepted as a branch edge. But now if these ones find out that this is the minimum cost outgoing edge, and then that could be a wrong thing, because it could be that for the integrated fragment this one is the minimum cost outgoing edge. So, that is why these nodes will also join in the search for finding the minimum cost outgoing edge, right. It is like this, that when I allow you to join me, I say that I am currently engaged in looking for the minimum cost outgoing edge from me, right. Now, you are part of me, so you also proceed to do that search, and in the whole thing including you and me, we have to find out the least weight outgoing edge. Yeah. So, that is why state P, the state P is also being sent along with the initiate message, right. Now, this is one case, this is the combination with rule A. Okay. We will see what happens when the processes receive the initiate message, we will see that in due course of time. Now, let us look at the other cases. If we find that L is not less than level P, then there are two cases, that L is equal to level P or L is greater than level P. Okay. Now, what we do is we check whether the status of the channel P is basic. Okay. If it is basic, then we will apply rule C and we will process the message later. If it is not basic, then we will apply rule B and then we will send an initiate message to Q with level equal to level P plus 1, and the name, remember what is the name of the integrated fragment for merging two levels, two fragments of the same level, it is the weight of the core edge, that is WPQ. Okay. And the status will become find, because now these two at the same level have merged, we need to again find the minimum cost outgoing edge, okay, least cost outgoing edge. So, the status will be find, right. This is going to be sent to Q. Now, how do we conclude here that this should be rule B application and this should be rule C? What is rule C? When is it applied? When the level is right. Okay. Now, why do we say that this is basic then? If it is basic, then that has happened. See, in this case what is going to happen is that both P will send this to Q and Q will send this to P. Okay. All right. They will have both found out that their outgoing least cost outgoing edges is this PQ, right, and they will change the status of the channel to branch, right. Okay. So, what does it mean? When you are testing an edge, when you are looking at the least cost outgoing edge, in that least cost outgoing edge, if the other side, when it gets the message, if it sees that this is a node of the same fragment, of a different fragment, the name is different, but the level is same, then you know that this is going to become a branch, right. So, in the pseudocode we will in due course of time we will come to that. Now, this is clear, 3 different rules of merging, and we have shown all 3 of them here. Upon receipt of the initiate LFS message from Q, this is what P is going to do. So, if the process P gets an initiate message, what is it going to do? It will first of all inherit the level of the initiate message, it will inherit the name of the initiate message, it will inherit the state of the initiate message, right. Right? Yes or no? And it will say that father P will be equal to Q. What is father P? Pointer leading towards the core edge. So, let us look at the 2 cases where the joining takes place. Case 1 is that the larger fragment, the smaller fragment joins with the larger one. So, let us look at this thing now, that this one was the core edge of the larger fragment. Okay. This was the larger fragment. This was the core edge. Okay. Let us call that Z. Now, this smaller fragment, this one has found that its least cost outgoing edge is from this node to some node here, right. So, it has sent a connect message from this P to this Q. What does Q do? Q sends a initiate message allowing it to join, right. Now, when this initiate message comes here, what is going to be the name of this fragment? WZ. The name of this will be WZ. The level of this will be the same as this. Now, what is going to happen is from P here, this whole tree will reorient itself so that this becomes the root of this sub fragment, and all the parents, the fathers are pointing like this towards the core edge. This is the core edge, and no change will take place here because they are already pointing to the core edge. Okay. This is what will happen when the initiate message reaches here. All the father pointers will now reorient itself towards the core edge. All right.
Core edge will be unrectified.
Core edge will be?
Won't have any direction to parent.
No, none of the edges have any direction.
The two nodes.
Joining the core edge. No, they won't have any. No. Okay. So that is going to be clear in due course of time. Okay. So we have everything pointing towards the core edge. So see what is happening when P receives the initiate LFS from Q. It inherits the level, it inherits the name, it inherits the state, and sets father P equal to Q because it is from Q that it received the initiate message. It will set the best channel of P to be undefined now. Why? Because the whole tree will reorient itself. So, I do not know which is the best in my subtree anymore. The best weight P will become infinity, and for all R belonging to neighbor of P such that the status of this is branch, which means along the tree. So, these are the tree edges, the edges for which the status is branch at the tree edges, right. So, along the tree edges except the one from which it got the initiate message, that is Q, we will send an initiate LFS to R. So, what does this mean? That the node P when it receives the initiate message, it will actually propagate the wave to all the neighbors other than Q from which it got that, right. It is going to send out the initiate LFS message to all of its other neighbors except Q, okay, and also only along the branch edges of the tree. It is not going to use the edges which are non-branch edges, only along the branch edges of the tree it is going to propagate this, right. Then it is going to check, after it has sent out these messages, it will check whether the state P which it has inherited from the larger fragment is find. If it is find, then it will start the finding process, and the finding process is initiated with a procedure called test, which it will start executing, okay. We will see in due course of time what the test is doing, right. Now, is this part, this is part 1, is it clear, right. So, we have what we have understood here is that by some mechanism a fragment determines that which is its least cost outgoing edge, that mechanism is the test mechanism which we are going to see now. After it determines that, a connect message is sent. When the connect message is sent, the node P on the other side examines if the connect message is from a smaller fragment. If so, it sends a initiate message down the smaller fragment to reorient the smaller fragment by inheriting its level, name, etc., and by making all of them point towards the core edge of the larger fragment, okay. Second case is when it gets a connect message from a node at the same level. In that case, each of the two nodes P and Q sends down initiate messages. P sends initiate messages towards Q, Q sends initiate messages towards P, and they all of them inform their subtrees that the new level is previous level plus 1, the new name is the name of this new edge, the weight of this new edge, and they all, their parent pointers now all point towards this new core edge, okay, right. These are the two cases. The third case is when there is a connect message from a larger fragment to a smaller fragment. In that case, the smaller fragment must wait. The larger fragment will have to wait. The smaller fragment will not allow the larger fragment to merge with it, right. So, how will the final merging take place? The smaller fragment at some point of time will discover that this is the best least best cost edge. Why will that happen always? Because you see, if you take any partition of the vertices, so your larger fragment is on this side, okay, rest of them are on the other side. Now, if from this you find out that this is the best cost outgoing edge, then from the other side also it has to be the best cost outgoing edge, right. So, these the fragments on this side will at some point of time discover that this is the best bridge to this side, right. Then there will be a connect message sent from this side, okay. Now, at that point of time you see the level of this will either be as large as this, will be the same, or it will be smaller, okay. If it becomes larger at any point of time, then this connect message will be processed by allowing this one to join into that. If this one becomes smaller and then sends a connect, then this one will allow it to join, and if they are equal, then they will join and make this as the new core edge, right. So, somewhere down the line that edge will be taken up, but we are purposefully not allowing the larger fragments to merge into the smaller fragments, to avoid certain concurrency problems. Those concurrency problems will relate out of the fact that the smaller fragment joins in the search of the larger fragment for the least cost outgoing edge. The larger fragment, if it also has to join the search for the smaller fragments, this thing, then we will have certain problems. Okay. I will come to that case and then explain what the problem will be. Okay. Now, okay, just let's see. Yes. Mm-hmm. Can a that will never happen. See what, remember how we started our initial discussion, that the algorithm works by finding a least cost outgoing edge of a fragment, and when all edge costs are different, then the least cost outgoing edge of every fragment will necessarily belong to the minimum spanning tree, right. So, once it is accepted as a branch, it can never be rejected later, it is part of the tree, right. So, only least cost outgoing edges of fragments are converted to branches, right, and when it is detected as a branch, then it can never get rejected in future, right. Similarly, if it is ever rejected, it means that it has become a front edge of the tree already. So, therefore, it can never become a branch. So, once rejected, always rejected, once it becomes a branch, it always remains a branch, right. Now, we are going to look at the ways of testing the edges. Okay. So, intuitively what we are going to do is that the node P will inspect its outgoing edges in increasing order of weight. Okay. What do we mean by inspect? It will try to determine whether that is an outgoing edge or not. So, to inspect edge PQ, P sends a test level P name P message to Q and wait for its answer. So, it is sending a test message to Q with its level and name. Okay. Now, what is Q going to do? If Q finds that P's fragment name is the same as Q's fragment name, what does it mean? It means that they are in the same fragment, right. So, therefore, this cannot be an edge at all of the tree, never in the future also. So, it will send a reject message and both P and Q will mark that edge as reject. So, the status of the channel from P to Q will be reject and the status of the channel from Q to P will also be reject, right. If the fragment name differs, then Q sends an accept message, provided that the third, look at the third case, the processing of a test LF message is deferred by Q if L is greater than level Q, because P and Q may actually belong to the same fragment, but the initiate LFS message has not yet reached Q. Now, please understand this issue. This issue is like this. This is one fragment, okay. This is another fragment. This has been selected as a branch. How was it selected as a branch? There was a connect message sent in this direction, and this one responded by sending a initiate, right. Now, this initiate message will now propagate to all the nodes here, right. Now, suppose at some point of time this node was engaged in searching for the least cost edge, okay, and its one node here send a test message to some node here, right. Now, this test message was sent and received here before the initiate message reached this node. Now, what is this node going to feel like? It is going to say that, okay, we are in different fragments, your name and my name does not match, but that is not actually correct, right, because it could be the case that this message is yet to reach here, and when it reaches we will have found that actually they belong to the same fragment. So, this edge should actually be rejected, but if we accept that, then we will create a cycle, right. So, that is why you see we avoid doing this thing by putting that partial order, that we say that the smaller fragment will join into the larger one. So, the smaller fragment, when it gets a test message from a larger fragment, it will not immediately respond, it will wait, because it is quite possible that this fragment is joining into that fragment, and therefore, its level will the name will actually change to the name of that. Okay. Is that clear? So, I think we have okay. Now, there is a further very simple optimization that is done here. Now, to inspect edge PQ, P sends a test message to Q and waits for an answer. Okay. Now, if Q finds that P's fragment name is the same as Q's fragment name, then it is supposed to send a reject message. Now, consider the case that if at that point of time Q had also sent a test message to P, both had sent tests to each other. Now, both know that it will be rejected. So, if you send a test message already, then you do not need to send a reject message again. Do you see what that means? P has sent a test message to Q, and Q has also sent a test message to P, right. Now, when Q gets the test message from P, it sees that our names are the same. So, this edge has to be rejected, but it knows that, okay, I have sent a test message. So, P will also be able to deduce that this is going to be rejected. So, why send another reject message, right. So, this is a simple optimization. So, if the edge PQ was just used by Q to send a test LF message, then P will know in a symmetrical way that the edge PQ is to be rejected, and in that case the reject message need not be sent by Q, right. All right. So, is it roughly clear that the way in which the testing of the edges take place, right? Now, yes.
Higher level, the process at higher level will not reply, or lower level will not reply.
You tell me which one will not reply. Whose levels will always increase, they can never decrease.
Higher level should be replied.
So, the one which is in a lower level, its level can increase and its name can change. the one which is at a lower level, that fragment's name can change and become the same as the name of the higher level. So, if the lower level fragment gets a request from a higher level fragment to test for an edge, the lower level fragment will say, I do not know at this point of time whether you and I are in the same fragment, because as of now your fragment name and my fragment name are different, but it is quite possible that my fragment is joining with yours, and then later on I will know that your fragment is actually my fragment, right. But look at it from the other point of view. When the lower level fragment sends a test to a higher level fragment, the higher level fragment knows that it will never be the case that I will join your fragment name. So, your fragment name will never become my fragment name, right.
My fragment name will become never your fragment.
No. I am getting a test from a fragment which is lower, right. Now, that one is asking me that are we in the same fragment, right. Now, what I can say here is that my fragment name is different from yours, and because your level is smaller than mine, it will never be the case that my fragment name is revised to your fragment name, right. So, it can send a accept, right. But remember that sending an accept does not mean that that becomes the branch edge. It is just saying that we are not in the same fragment, but out of these edges we still have to find out the least cost edge from the whole fragment and then use that to connect, right. Unfortunately, we have run out of time. So, that part of finding out the least cost edge and connecting will be taken up in the next class.